we're ready to start solving exponential equations. And you're probably going, well, we solved those earlier in the chapter. We did. We solved exponential functions like the one you see on the left, where we had 4 as a base and 8 as a base, and we said, oh, well, I can solve that just fine as long as I change them to a common base. And so you changed 4 to 2 squared, and you changed 8 to 2 cubed, and you proceeded to then multiply the exponents, and finally say, oh, if my bases are the same, my exponents are the same, and you solved the problem. Okay, that's all fine if you can make common bases. But most of the problems in the real world, and that's where we're headed, is toward real world applications, don't come with numbers that make perfect little common bases like that. Instead, we get numbers like you see here on the right. Now we have 13 as a base, 2,150. I don't think we're going to find a common base between those. So now we have the problem of, oh no, what do we do if we want to solve this type of an expression? Well, in this case, we need some way to solve for x and get it down out of the exponent. We can't solve for x when it's an exponent if we can't make common bases. So what rule do we know that allows us to bring the exponent down from that position? And of course, yes, it's that ever-present, ever-famous plug rule. But in order to use that rule, you must put a log on both sides. So you may recall we once called this logging and plugging. We take the log of both sides, and then once I have the log of each of those quantities, I can then use the plug rule and say, oh, well, now I can take the exponent down front. Now here's a very common error that occurs, though, when doing this. Do I have that expression written correctly? I pulled the 2x plus 3 down front, but now it looks like it's 3 times the log of 13, but in reality it's supposed to be the quantity 2x plus 3. So it's really critical that when you bring that down, if it is a quantity, you need to keep it in the quantity. Now our goal is to simply solve for x with normal algebra. There are 2 methods you can do this, but one I definitely recommend. I could distribute the log of 13 into both parts here, but that just makes more logs and more confusion. So while it will work and you can do it, it tends to lead to more algebraic errors. Instead, I really don't want to mix the log with the 2x plus 3, so instead I'm going to choose to go, well, I don't want it over here, so I'm going to divide it out of there by going, oh, let's divide by the log of 13. That will cancel it on this side. Over here now, I also have the log of 13. And I probably should be more properly correct by saying the log of those and keep them in parentheses so you realize they are inside that logarithm. Now I have 2x plus 3 equals this lovely log expression. And how would I get x by itself? Well, yes, indeed. I need to subtract 3 and divide by 2. It's just a matter of where do I put those numbers? Well, you can't subtract it from the numbers inside the log. So you're going to keep your log as is, log of 2,150 over log of 13. We're going to have to simply subtract 3 back there and back. And then, likewise, if I want to get rid of the 2, I'm going to divide both sides by 2. And if I do that, then that's going to put this whole thing over 2. That makes for a bit of a nightmare. I know you could actually turn those numbers to decimals as you went. But if you turn each of those logs to a decimal as you go, you're going to round it off each time. And so every time you do you convert it into a decimal and round it off, you're creating error in your answer. So instead, since you have these wonderful calculators that are quite capable of doing this, you're simply going to have to put in a fraction and then put in the top another fraction. So you're now going to have a fraction in a fraction tack your minus 3 on the end. So you can't, it's not that hard to type in a calculator, and if you do so, you will get a lovely answer like negative 0.0042. You're going to round answers to 2 significant digits. So in this case, the zeros were placeholders, so we had to go 4-2. And we have solved an exponential equation. Well, if you thought that was fun, you haven't seen anything yet. So let's try the next one. This next one is one that you did not do in Algebra 2, or actually in pre-calc for that matter. But the college algebra people think it looks like fun, so hey, let's go for it. Now, you'll notice, what's the big difference between this problem and the one I did in the past? That last problem only had an exponent on one of the terms, not on both sides. Now we have 5 to the 2x plus 1, 3 to the x minus 1. So that makes a huge difference because I have an exponent on both sides. But still, we're going to apply the same general method. We're going to log and plug. So I am going to take first the log of both sides, because you cannot use the plug rule unless there are logs involved. And then what am I going to be able to do with those exponents? Absolutely, I'm going to pull them down front. I'm going to have 2x plus 1 in parentheses times the log of 5, and I'm going to pull the x minus 1 down front times the log of 3. Well, unfortunately, here's where things get a little more messier here. Will it do me any good to divide one of the logs to the other side? Since I'm going to have to take these times one of those quantities. Unfortunately, no, there's not an easy way to do this. We actually have to do all the algebra, and indeed we can't avoid it. We have to distribute here. So we have to take the log of 5 times both of those expressions and the log of 3 times both terms in that quantity. So if I'm going to do that, I'm going to have then 2x times the log of 5. Then, of course, 1 times the log of 5 is going to give me the log of 5. On the other side, same thing. I'm going to have x times the log of 3, and I'm going to subtract and have minus 1 times the log of 3. Well, what do I do from here? I look at it and see, well, my goal is to solve for x. And as you were taught back in Algebra 1, if you want to solve for x, you get everything with x in it on one side of the equal sign, everything that does not have an x in it on the other side. So I'm going to put all the x involved terms on the left side, which means I'm subtracting over that x times the log of 3. And then I'm going to take all the other terms to the right side, which means I'm going to subtract the log of 5 over and still have minus the log of 3. Well, not pretty, but doable. All right, the step that usually stalls people. They get to this point and it's like, well, okay, how do I solve for x? Because my x's are mixed in with all those logs. What am I going to do with it? Well, it's our good friend, the common factor. You'll notice here on the left that x is a common factor. So once you get to this point, you actually factor the x out front, which leaves you 2 times the log of 5 minus the log of 3. And the other side, of course, is going to just hold steady. You actually, by the way, though, do have a choice on some of these. You could combine some of these. And in fact, we are going to combine them using our log properties. So I don't really want to have all these logarithms. It is possible that you could divide it over, but I'd like you to use log properties and go, hey, look, I can take this 2 and move it up here and make that 5 squared. So now I have x times the log of 25 minus the log of 3. What are you allowed to do when you have logs that are subtracted? You're actually allowed to change that into the log of 25 thirds. So now I've taken that messy expression down to a single log. Okay, on the other side, I want to do the same thing, but what wrinkle do I have? Well, this negative on this front term just kind of really messes things up. And since they're both negative, what I'm going to do is I'm actually going to factor that negative out front, which is going to make me have the log of 5 plus the log of 3. What do you do when you have logs that are added? Yes, indeed, you multiply, so that becomes the log of 15. Now, my ultimate goal is to get x by itself. What do I need to do that? Well, now I can just divide over the log of 25 thirds and punch this baby in my calculator. So that would be this lovely expression, and once you punch it in, you will get a negative 1.28, and I should have an approximate symbol on that, because it is indeed a very approximate number. Now, is there a need to check these kind of answers? Well, if you look at your original problem did not contain logs. Any number can be an exponent, so no, you don't need to check these. Boy, howdy, wasn't that a fun one. All right, moving on then. Let's look at some problems that involve e's. E's are actually our friend because we know that getting things to work with e just involves adding a natural log in places. But the question is, when can I add a natural log? I want to solve for x up here in the exponent. So the question, I know natural log will cancel out the e, but can I put it on there right now? If I added a log right now, I'd have the log of 7 times e. That's not possible. You can't have that. You have to have the e all by itself. So the first thing you are always going to do, if there is a coefficient on an e, you will always immediately divide that coefficient out of there. So that's going to give us e to the 4x minus 2 equals 21. Now, once you're to that point, then you can go ahead and do the log of both sides. So now I can add a natural log of e to the 4x minus 2 and a natural log of 21. What's going to happen? Natural log and e are going to cancel. I'm going to have 4x minus 2 equals natural log of 21. And it's now a pretty easy solve. I can add 2 to the other side and divide by 4. Once I do that, I turn again to my calculator and discover that its approximate value is 1.26. So, particularly a problem like that, no major big event. Okay, this one on the right looks a little more complicated, but it's mostly because it's set up in that fraction and the e's in the denominator. This is actually the equation of a logistic function. If you've had pre-calc, you've talked about logistic functions, quite frankly. At the moment, I can't remember if we did them back when we were doing regressions with logarithms, or excuse me, when we were doing regressions, and we wanted to fit things. Logistic functions are very common in the real world and with nature. Logistic functions, when graphed, start out slowly, start to rise quickly, and then level off again. And this particular expression with the e to a variable power in the denominator is their identifying characteristic. They're very popular in the business world because they often model the growth of a business. A business starts to grow slowly, it's growing slowly, then business picks up, business really grows, but then there comes a point when you've probably reached your maximum audience, maximum production, and your business levels out again. Businesses, of course, love to know, that's really an asymptote up there, they love to know where that leveling out point is going to be so that they don't waste resources trying to increase their production perhaps when they know their business is going to level out at a certain point. So in our case here right now, we're not worrying about it being a logistic function at the moment. We just want to be able to solve for e. Later on, we might look at this as a real world problem and try to actually solve certain portions of it. What we have here then is I need to solve for e. How can you solve for e when it's in the denominator? Well, the answer is, of course, you can't. You don't want it in the denominator. So I immediately want to multiply it to the other side. Now, since I'm a little bit out of room here, I am simply going to multiply it to the other side and say I have 120 times 1 plus 2e to the negative 0.5x. Note, you cannot add that 1 plus 2 and make 3. Okay, so the question is, do I want to distribute the 120 or divide the 120 back over? Well, we prefer to get as few terms as possible with our e, so yes, I'm going to opt to divide the 120 back to the other side, which is going to reduce to 37/12. Okay, now it's just a matter of working a problem like we did the one on the left. We need to isolate the e so that we can add natural logs to it. How do I isolate the e? Well, first thing I would do would be subtract 1, which would be 25/12. Lost my x up there. Now I'm down to 2e to the negative 0.5x. Am I to the point now that I can add natural logs? And still no. I got to get rid of the 2, so now I need to divide by 2. Which, remember, dividing by 2 is the same thing as multiplying by a half, and since I'm dealing with fractions, that would be smarter. So now I have 25/24 equals e to the negative 0.5x. At long last, I am finally to the point, e is isolated, I can actually now add my natural logs to both sides and bring that baby down. So I'm going to have the natural log of 25/24 and the natural log of e to the negative 0.5x. Of course, on the right-hand side, natural log and e are going to take each other out. And now I have a negative half x equals a natural log of 25/24. And finally, divide by the 0.5, the negative 0.5, excuse me. And what would we do without our calculator to generate these final lovely numbers that we're going to get out of this thing? And I'm actually disagreeing with the answer I have on my sheet because I did not go to 2 significant digits. So the big question is here, as I replug this in, does it really round off to that, or did I not write the right number down? Yep, I just didn't write more digits. And so it should actually be negative 0.082 would be our proper value for x if we're going to 2 significant digits. So while it looks kind of messy and intimidating, it's really not that bad. Okay, moving on. This one will cause trouble. It's actually really easy, but man, do I have people blow this, particularly in pre-calc, because you look at it and you go, oh, I've got to add natural logs, I've got to use natural logs, I've got to get those x's down. But you can't do that because you can never go take the natural log of individual terms. It's illegal. You can't do that. You can only do the natural log of whole sides. So, whoops, sorry. If I can't add natural logs to each one, what on earth do I do to this thing? Well, believe it or not, you notice you have e to the 2x and you have e to the x. That's like having x squared minus 4x equals 12. How do we solve quadratic equations? We set them equal to 0 and we factor them. So that's exactly what you're going to do here. You're going to bring this thing over, you're going to set it equal to 0, and you're going to factor it. So if I break it into parentheses, e to the 2x. Well, it's not nearly as complicated as you think. E to the x and e to the x. What do we do to exponents when we multiply? We add them. So if I multiply those two e's together, that's x plus x, and it makes 2x. Okay, I need factors of 12 that'll get me a 4. So that's got to be 6 and 2. I need a negative 6 and a positive 2 to get a negative 4 in the middle. So it factors like a normal old equation. Now you proceed to solve each factor, and then we'll be able to throw our natural logs into the mix. So if I add 6 over, get e isolated, of course, and then I can take the natural log of both sides. Well, in this case, what's going to happen? Well, I'm going to end up with x equals the natural log of 6, or its decimal equivalent, which is about 1.79. Here on the right-hand side, if I do the same thing, if I take the natural log of both sides, what's going to happen? Well, I have the natural log of -2. Can I have the natural log of a -2? Of course not. So that baby's out of there. You can't do the log of a negative number. So in this case, we only have one solution. Okay. Well, I know you enjoyed the last lesson, which is short. This one's a little longer. We got 2 problems to go here. This particular problem, toward the end of the assignment, they're going to ask you to solve a problem by calculator. And if you look at this, quite frankly, it's the only choice you've got, because who on earth could solve that by hand? Quite frankly, I don't know of any way to solve that thing by hand. It's a nightmare. So how do we solve it by calculator? Well, we're going to solve it with a graph. You've done this many times. Hopefully, you're out there going, oh yes, I'm going to put this function in F1. I'm going to put this function in F2. I'm going to graph them. And where will the solution be? Where will they equal each other? Of course. They equal each other at the intersection point. And we have found intersection points many, many times. I have that set up real fast. Here's the left function. I'm going to turn it on, and you're going to see it's quite an interesting graph. If I arrow down, here's F2. I'm going to turn it on. That's the right-hand side of the equation, and we're looking for the intersection points. How many intersection points are there? Well, we can see there are 2. So I simply need to go do an intersection. So menu, analyze graph, intersection. Let's get on the left side here and hit enter. Go to the right side, connect. There's one intersection point. If I do it again, I can, of course it moved the wrong direction. Keep going right. Come on. There, hit enter, move across, get my intersection point. There's another intersection point, enter. See if I can get that one to drag out of the way as well. And ta-da, we have answers of -1.94 and positive 1.71. Gotta admit, pretty slick. Now, why did I choose to use the x-coordinates as my answer? Because I was trying to solve for x here. So my x-coordinates would indeed be my solutions. That was x equals -1.94 and positive 1.71. So, solving by calculator, a thing of beauty. Last but not least, at the end of this assignment, there are a few problems where they're starting you to work toward real-world applications. They're not full-out ones like they're going to be next class. But the one I want to talk about, because we really haven't gotten to do it before, is Newton's law of cooling. And you'll notice it's got some pretty funky terms. This formula is on your formula sheet, so be sure to use it. Okay, this is the law that tells us how fast things cool off. If you take something hot and you put it in a cooler temperature, it cools down. It can actually be done in reverse. You can also put it in something cold in a warmer area and it will warm it up by this same particular formula. Now you have to learn the values here because unfortunately there's a lot of variables. You're talking about 2 temperatures. You're talking about the temperature of the substance you're studying and you're talking about the temperature of the air. Okay, the capital T's are the air temperature around it. Both capital T's. The mu's, little lovely Greek letters, those are the temperature of the actual substance you're studying. Since this one here on the right has a subscript of 0, we know that is the initial temperature. And plain mu here on the left is the final temperature of the substance. Now this can, in our case, we're about to cool off a bowl of soup. This can be cooling, anything warm or cool, including, within certain time limits, figuring out how long a dead body has been dead if it's been in a certain air temperature. This is one of the things they use in forensic science to determine how long someone might have been dead. There are limits, though, on how long this could go. Okay. K is going to vary based on the substance you're studying. So if your soup is going to be different than coffee, which is going to be different than a dead body. So K is what we call, it's just a constant, the constant of cooling. And then T is, of course, the amount of time this all takes to happen. That's, of course, more than one T. That's why they had to use capital T's for the air temperatures. Okay, on today's assignment, they're just simply going to ask you, can you fill this in and solve for a certain variable? So in our case, we have a bowl of soup here that's been just heated up, and it's at 200 degrees Fahrenheit. It's taken into a room that's 70 degrees Fahrenheit. And the question is, how long will it take it to get down to 100 degrees Fahrenheit? Now, K, in this case, they're going to give it to you. Next class, I'm going to make you find K. But right now, I'm going to give you K. So we can go with filling in this formula. And I'm going to rewrite it here, just so I have it in front of me. Okay, I'm just working left to right. Do I know the final temperature that the soup's going to end up at? And the question was, yes, when will it be at 100 degrees? Okay, capital T is air temperature. Air temperature is 70 here. I'm going to put that number in both capital T's. Mu naught is the initial temperature. The initial temperature, how hot was the soup to start with? It was 200 degrees. Of course, E remains E. K they gave to us 0.4855, and that is negative. It has to be negative if it's cooling down. The negative is what's making it decreasing. And then the big question is the time. How much time does it take to do it? So now we're to the point we simply need to solve for T. Now, it looks a little messy at the moment, but if you go clean it up slightly, this is no big deal. The key thing is that parenthesis. That's 200 minus 70. So in other words, that's 130 times e to this lovely decimal number, t. Okay? How have we solved every other e problem we've done? We isolated the e. What must we move first? And in this case, it is a little different. Yes, you're going to have to get the 70 out of here first by subtracting it, which is taking us down to 30. So I have 30 equals 130e to this great number. Now I need to divide by 130, which will take me down to 3/13. And e is finally isolated, so what are we going to do? Of course, our favorite thing of all, we're going to add natural logs. So now I have the lovely natural log of 3/13. The natural log and the e are going to cancel, so it equals the great decimal number here. If I then divide the decimal out and go to my handy dandy calculator, I'm trying not to have to extend the board so that the notes will be more readable. So coming over this way, once I punch that into my calculator, I'm going to get somewhere, when I find my lovely answer, 30.2. So what does 30.2 mean? That's the question. Well, you have to go back to the problem. We solved for time, so that's a time situation. And actually, I guess I didn't do a good enough job writing the word problem because I didn't tell you that this equation was written in terms of minutes. So I should add that. This was how many minutes will it take, because the constant was originally calculated in minutes. Once we start doing this for ourselves and solving for k ourselves, there won't be a problem with that. So in other words, in about 30 minutes, this soup's going to have dropped to 100 degrees. Now that doesn't sound that's 100 degrees sounds fairly hot when we think of air temperatures outside, but if you think in terms of soup, that's not all that warm. Our bodies are at 98.6, and to me, my body's a little lukewarm to be eating soup, so you would definitely like your soup warmer than that. Okay, there you go. That's the thrills and excitement of exponential equations. There's lots of good stuff and tons of real-world uses for this. We're going to be spending several days on the applications, so get pumped.